Alright everybody, what's going on? This video we're going to look at double integrals over rectangles. So let's go ahead and get started. Alright, so just to recall back when you were doing the first calculus, or maybe second calculus for some of you, but probably first calculus. When you first started learning to do integrals, we had a curve, okay? And remember, you would break that curve up into rectangles, and we would find the area of each of the rectangles of each rectangle and then add those areas up, and we could approximate the area under the curve. And remember, you had the width of the rectangle, that was delta x. The height was f of x star sub I. And now that was basically you would evaluate the function at this x value to get the height, and then you would just sum those heights up. You would sum the height times the width. Okay, so you would multiply the height times the width. That would give you the area of the rectangle, and you would sum those up from, and you know, that was between A and B. All right. And then you know the integral, we had the integral from a to b of f of x dx was equal to the limit as n goes to infinity. Remember, n represented the number of rectangles you used, and the number of rectangles would go to infinity, and we would sum the height times the width up from I to n, and n goes to infinity. All right, so that's just a quick reminder of what you were doing. All right, so now let's consider a function f of two variables defined on a closed rectangle, where the rectangle R, that's from AB by CD, where we have a point xy, which is an element of R2, and x is between AB, y is between CD, and we first suppose that f of xy is greater than or equal to 0, then the graph of f is a surface with equation z equals f of xy. Let S be the solid that lies above R, above the rectangle, and under the graph of f. Okay, so it's like a prism or something, or a rectangular solid. Under the graph of f, that is, S is a point xyz, which is an element of R3, where z is between 0 and f of xy, where xy is an element of R. Okay, and when I say R here, that means this point is in that rectangle. Okay, and I'm going to draw a picture of all this so you can see it, but we just read through what it says. All right, so let's take a look at this right here. All right, so let's suppose, let's see if we can't. All right, now let's see. Let me try to draw this. So we got a surface here. Try to draw it the best I can. And so all right, so you see we've got this surface here, and this right here should be lined up with this, but I know it's not, but Oh well. But that's what we have. We have a surface. And this surface here, this is your z equals f of x, y. This is the z-axis, the x-axis, and the y-axis. And we've got here, this is your A to B. This right here is your C to D. That's the rectangle, AB by CD. This is your rectangle, R. Okay, so that's what we have here. That's what they're talking about. And it's actually like you have a, and I know I'm gonna butcher this when I draw it, but it's kind of like you have a, I guess something like this. I know that's not the best, but anyway, it's like this little rectangle here, okay? And you're going to have these little prisms coming up, and we're finding these volumes here, and we're gonna sum up the volumes. I'll talk about that more in just a minute. But that's what we're looking at. All right. So what we'll do here is we'll divide this AB, and I'm going to draw another picture of what I'm writing down, but we will divide AB into M sub intervals. And we will divide CD into N subintervals. All right, and that'll give us when we divide them into the subintervals, we'll have a delta x is equal to b minus a over m. We'll have a delta y is equal to d minus c over n. All right. Now let's draw a picture illustrating this. So basically what we're going to do here, the picture I'm fixing to draw, is suppose we were standing up here and we're looking down. And what would we see? We would see a rectangle or a square, whatever it is. So what we have here is all right. So let's draw. Let's see. Let's draw this. Draw this a little bit straighter. All right, so we got however many of these you have. All right, and these vertical lines here, they should be evenly spaced. Maybe I can do a little bit better job of that. Okay, so that's what we're doing. We got the rectangle and we've broken it up into M and N subintervals. Okay, and so this right here, this is some point y sub j, or this y value is y sub j, this is y sub j minus 1, and the distance between those is delta y. And then same thing here. Along the x, we got x. We got x sub I minus 1. We've got x sub I. And this distance between them is delta x. All right. And of course, this right here is going from A to B. This is going from C to D. Okay. And this is your x-axis, and this is your y-axis. All right. All right. So if we want to find, we may want to find the volume of a box. So in order to get the volume of the box, and let me label a few more. We can use upper right corners. Okay, see this little square here? We're using the upper right corner, and I'll explain that more in a minute also. But, and then we got a point here. All right, so this we could label this x sub I, y sub j. You know, we have some sample point in here too. We could have that. So that's x sub I star, y sub j star, and this would be a rectangle. This would be our rectangle r sub ij. Okay. And this right here represents the height of the box. Okay, that would give us the height of the box. All right. So we've got volume of box is the height of the box times the area of the base rectangle. So it would be, so if this box, see like up here, all right, this box here, it would be the height of the box times the base area of this rectangle here. All right, so it's the height, which is f of x sub I star y sub j star times delta A. That's the area, and delta A is equal to delta x times delta y. See, this right here, and I guess I maybe should have moved this down, or could have moved this down some, but oh well. But what it is see the width of this box is delta x, the height of that box is delta y, so delta x times delta y, length times height, that gives me the area of a rectangle. All right. And then adding the volumes, or adding the volume of all boxes, we get an approximation. And I'm going to do examples of these to the total volume of S, where we have the volume is equal to the sum I equals 1 to M. It's a double sum here. J equals 1 to N of F of X sub I J star Y sub I J star times delta A. And this right here is a double Riemann sum. All right, so I don't know if that made a whole lot of sense to you, but we're going to do some examples. It's similar to what we did with when we were in single variable calculus, and we found the area of the rectangles and we added those areas up. Now what we're doing is we're finding the volume of these boxes and adding these volumes up. Okay. All right, so let's look at this definition. All right, so the double integral of f over the rectangle R is, and so we've got the double integral over R of f of xy dA is equal to the limit as m and n go to infinity of f of x sub I star y sub I j x sub I j star y sub I j star times dA, if this limit exists. And if f of xy is greater than or equal to 0, then the volume V of the solid that lies above the rectangle R and below the surface z equals f of xy is V equals, and it's the integral, the double integral, f of xy dA. So we're finding the volume below a surface and above the rectangle. Okay. And I showed you in this sketch up here. See, and basically, we're going to have a bunch of boxes up underneath here, and we're adding all these volumes up, and that's going to give us this volume that's below this surface here and above this rectangle, this volume right in here. All right, so let's come over here, and we've got us an example to do. All right, so it says estimate the volume of the solid that lies above the square R 0,3 by 0,3 and below the elliptic paraboloid z equals 20 minus x squared minus y squared. And it says divide R into 4 equal squares and choose the sample point to be the upper right corner of each square, R sub I j. And that's what I was showing you up here. See, you can have a sample point here. I mean, you could have a sample point anywhere in that rectangle, but it would be stupid to pick one like right here. Okay, well, you wouldn't want to do that. You would want to pick like a corner or the midpoint of it. You see that? So in this problem, they're asking us to divide it into 4 equal squares and choose the sample point to be the upper right corner of each square R sub I j. So let's draw a rectangle. We don't really need to draw the surface here. We just need to look at the rectangle in the XY plane. All right, so let's do that. All right, so there we have that. Let's see if I can go 1, 2, 3, 1, 2, 3. Try to make it as uniform as possible. All right, so I've got 1, 2, 3, 1, 2, 3. Now, it says to break it up into 4 squares, 4 equal squares. Divide R into that. All right, so that's going to be right between 1 and 2. All right, so there's my 4 equal squares. And they want us to use upper right corners. So see this square right here? I'm going to use the upper right corner. And this square right here, I'm going to use the upper right corner. And then this square here, the upper right corner. This square right here, the upper right corner. And this would be my rectangle R11. This would be R12. This would be R21, and this would be R22. There's my rectangles. And then what I think you might want to do also, which I think would be helpful when you're putting all this stuff in, is label these points. So this would be the point 3/2, 3/2, right? Because we're right in the middle of 1 and 2, so that's, we go over x is 3. See, this is 3/2, and this is 3/2. All right, and then what would this point be? It would be 3/2, 3, right? So this would be 3/2, 3. This point would be 3/3, 3/3, and this point would be 3/3. All right, and we also have f of xy is equal to this, 20 minus x squared minus y squared. So that's 20 minus x squared minus y squared. All right, so what is the height of this rectangle right here? Okay, well, I take this point, plug it in for x, y, and that gives me the height at that point. Okay, and that would be the height of this box right here, or prism, rectangular, solid, you know, whatever you're going to call it. Prism, I guess. All right, so do we know what m and n are? Because I need to get what? I need to get delta x, and I need to get delta y, and I need delta a, right? All right, I need the area of each one of these boxes. Well, I mean, obviously we know that the width, this m here, that's 3/2. N would be 3/2. But let's write it out. Okay, let's write it out so we can see all this. So I know I've got m is equal to 2, n is equal to 2, right? M, see, I'm dividing it into 4 equal rectangles. So here's my 4 equal rectangles right here. I've got 1, 2, that's m. See, I'm breaking this in half. I'm breaking this in half this way. So m is 2, n is 2. All right. So now let's get delta x. That's, remember, b minus a over m. So b, which is 3, minus a, which is 0, over m, which is 2. So that's 3/2. And then delta y, that's the same thing. That's d minus c. So d is 3 minus c, which is 0, over n, which is 2. And that's 3/2 also. I mean, yeah, we can see it from the picture, but let's write it out so we can see it. And then I also have delta a. Remember, that's delta x times delta y, which is 3/2 times 3/2, which is 9 over 4. That's delta a. All right. And then remember, oh, I'm running out of room, aren't I? I need to maybe let me move this. All right. Now, I need the volume, right? So the volume is equal to the sum I equals 1 to m, which in this case is 2, j equals 1 to n, which is 2, f of xy times delta a. All right. So basically what I'm going to do is I'm going to do delta a times the height at this point plus delta a times the height at this point plus delta a times the height at this point plus delta a times the height at this point. So I'm going to get my volume. My volume is going to be 9/4. That's delta a. Here's my delta a right here. Times the height at this point. So I'm going to take the 3/2 and plug it into here. So that's times f of 3/2 plus 9/4 times the height at this point. So I'm going to plug this into the function. So that's f of 3/2 3 plus 9/4 times f of, and then we'll do this point. I mean, it really doesn't matter. You're adding them up. And so at this point, that's f of 3/2 plus 9/4 times f at this point. All right. So there you go. Now, I hope that all makes sense to you. Okay, and you can see it's similar to what you did before when you added up the areas of those rectangles. We're just adding up the volume of the boxes now. All right, and so I'm going to get, now you see the 9/4, I can actually just factor that out. Okay, and then when I plug this in for here, so I'm gonna show you here. See, we got f of 3/2. I'm not going to do it on any of the other ones, but that's 20 minus 3/2 squared minus 3/2 squared. Okay, so I plug this into x and y, and that gives me 31/2. And then I plug this one in, that's going to give me 35/4 plus, and then I plug the next one in, that's going to give me 35/4, and then I plug the last one in, that's going to give me 2. And so this is going to be 315/4, which is about 78.75. And that's the volume under that curve, but above this rectangle right here. And that's using upper right hand points. Okay. All right. Now, let's look at this. We want to do the previous example, but we want to use midpoints. Okay? Previous example, but midpoints. So everything's the same, except instead of choosing upper right corners, we're going to choose the midpoints of these squares. All right, so let's draw this again. All right, so I've got 1, 2, 3, 1, 2, 3. And hopefully you can see why we're going over 3 and up 3. That's because that's what they give us, 0, 3 by 0, 3. Okay. All right, so let's draw this in here. All right, and we've got our 4 equal boxes. 4 equals squares. All right. And this is R11, R12, R21, R22, and we are choosing midpoints right here. All right. And of course, we've got the same thing. We've got M is equal to 2, N is equal to 2, and I think we had delta A, that was, what was that, 9/4. See, all that's the same in our function. We've got f of x, y is equal to 20 minus x squared minus y squared. I think I wrote everything down. Yeah, and of course we know what delta y, we found delta y and delta x. Okay, they're each 3/2. None of that's going to change in this problem. All right. All right, so now, like I said, what I would do is I would label these points, and keep in mind here, let me get another color. Keep in mind this is 3/2. This is 3/2. Now I'm going halfway between 0 and 3/2. What is that? That's 3/4. Halfway between 0 and 3/2, that's 3/4. You see that? All right, so this is the point 3/4, 3/4. All right, now what's this value up here? This is going to be 9/4. See, I'm halfway between 3/2 and 3. You see that? Halfway between 3/2 and 3. So if I got 3/2 plus 3, that equals what? 9/2. And then I got a half that, and that gives me 9/4. So that's the 9/4 right there. Remember finding the midpoint between 2 points? You just add like if I want the midpoint between 3/2 and 3, I just add them up and divide by 2. All right. And of course this would be 3/4. This would be 9/4. All right. All right, so what is this? Well, this is going to be 3/4, 9/4. This is going to be 9/4. 9/4, 9/4, and this is going to be 9/4, 3/2. Okay, like I said, just go ahead and go through there and take the time to label those points. Just it's going to be quicker for to plug them into the function. All right, so now let's find our volume. So remember, the volume, that's delta A, which is 9/4, times the height at this point, plus delta A times the height at this point, and so on. Now, remember what we did in the last problem? We factored out that delta A. And so that's what I'm going to do here. I'm going to go ahead and factor out that delta A. And so then all I have to do is add up the heights. And so that's going to be f of 3/4, 3/4, plus f of, let's see, 9/4, 9/4, 3/4. Oh, I didn't. This should be a 4, not a 2. All right, so I've got f of 3/4, 9/4, this one up here, and then plus the height of this rectangle, f of 9/4, 3/4, plus, and then the height at this point, f of 9/4, 9/4. All right. And so that's going to give me 9/4 times, and then when I plug this in for x and y, that's 151/8 plus, and then the next point, that is 115/8 plus, and then I plug in the next point, 115/8 plus, and then I plug this point in, that's going to be 79/8. And when you punch all that in, you get 1035/8, which is 129.375. And you can see, you see how big of a difference we are. Okay, you see how big of a difference this is. Look what we got when we use midpoints. We got 129.375 versus getting 78.75. We're about just about 60 off, or 56, about 50, closer to 50 cubic units cubed. Okay. This, and remember, this is a box. This is units cubed. Whatever the unit is, cubed. All right. So there's the one using midpoints. There's one using upper right corners. Okay. So let's see what the next example. So previous example. Okay. So same function as the other two, but here they want us to use 9 squares in upper right corners. Okay. So let's see what that gives us. I'm going to have to maybe draw this one a little bit bigger. All right. 1, 2, 3. 1, 2, 3. All right, so let's divide this up. Now we're dividing this up into 9 equal squares. So we're going to have, we'll actually have more here. Now, so some things are going to change. Okay. For one thing, m is going to change. So m is equal to what? We got 1, 2, 3. N is equal to 1, 2, 3. All right. So here I've got delta x is equal to 3 minus 0 over 3. See, b minus a over m, which is 3. That's 1. And delta y is equal to d minus c, 3 minus 0 over n, which that's 1 also. So we've got delta a, remember that's delta x times delta y, which that's going to be 1 times 1, which is 1. All right. So they asked us to use upper right points, upper right corner. So here's our points right here that we're going to evaluate. And let me go ahead and label these. We got R11, R12, R13, R21, R22, R23, R31, R32, and R33. Now, remember what I told you. Let's go ahead and label our points. So this would be the point 1, 1. This would be the point 2, 1. This would be the point 3, 1. This is the point 2, 1, 2, 2. And this would be 3, 2. This would be the point, and I'm sorry, this right here would not be 2, 1. It would actually be 1, 2, wouldn't it? All right, and so then this is 1, 3. This is 2, 3, and this is 3, 3. So let me make sure I labeled all these right. 1, 1, 2, 1, 3, 1. Then I've got 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, and 3, 3. And once again, remember our function is f of xy equals 20 minus x squared minus y squared. All right, so I've got the volume is equal to, so there's my delta A times, and then I'm going to sum up the heights. All right, so I've got f of 1, 1, this point, plus f of 1, 2, f of 1, 2, plus f of 1, 3, plus f of 2, 1, plus f of 2, 2, plus f of 2, 3, plus f of 3, 1, plus f of 3, 2, and then plus f of 3, 3. All right. And so each one of these points you have to plug in for x, y. And let's see what that gives us. So we get v is equal to 1 times, so this is going to be 18 plus 15 plus 10 plus 15 plus 12 plus 7 plus 10 plus 7 plus 2. And that's going to be 96. And you can see the 96 here actually gets closer to the 129. It's closer than the 78.75. All right. So and you know, if we did the 9 squares here with midpoints, we'd probably get even closer to the or possibility that we get even closer to the actual volume. And remember, this is approximating the volumes. Okay. All right. So I hope all that made sense to you. That's approximating these volumes under a surface, but above that rectangle. See that the surface. See this rectangle here. The surface is above this rectangle. All right. All right, so let's look at this. Iterated integrals. So we've got the double integral a to b, c to d of f of xy, dy dx. All right, so what do we do here? Well, first we integrate with respect to y. So we got the dy right here, holding x fixed from y equals c to y equals d. Okay, see, from c to d. And then we integrate the resulting function of x with respect to x from x equal a to x equal b. And then you can see here, this is the same thing, except we're integrating with respect to x first, and then we're integrating with respect to y. All right, and so it's pretty much the same thing. First, integrate with respect to x, holding y fixed from x equal a to x equal b, and then integrate the resulting function of y with respect to y from y equals c to y equal d. All right, this is double integrals, and pretty soon you're going to get into triple integrals. Okay, but let's figure out how to do double integrals first. All right, so we want to evaluate this. So what do we get? Well, let's look. All right. So what I want to do is I want to integrate this thing with respect to y, holding x fixed. So I kind of want to treat x like it's a constant, like it's a number. All right. So just think of this. You see, we got x squared y. Well, what if we had 5y? Okay. Pretend like this 5 is this x squared. So what would be the integral of that? Well, that would be 5/2 y squared, right? That's all it is. So you're treating this x squared like this 5. That's all it is. It's don't try to make this complicated, because it's really not. All right. So this is going to be the integral 0 to 3, and look, I'm integrating this. Okay, that's what I'm working on right now. So this is going to be x squared over 2 y squared. Remember, you add 1 to the exponent and then divide by that new exponent. So add 1 to the exponent, that's 2, divide by that, that's a 2. Okay, that's all we're doing. All right, and so that's this, and that is from what? From 1 to 2. See, we're evaluating it from 1 to 2, and then dx. All right. So now I've got to do this part. I've got to work on this part. I've got to evaluate that. Okay. Pretend like this and this are not even there right now. That's all you got to do. And so this is going to be 0 to 3, and that's going to be x squared over 2. Now, I should have done this a little better. This probably help you here. Y equals 1 to y equal 2 dx. Okay, I would, go ahead and put y equals 1 to y equals 2, so that way you know that you're plugging these numbers in for y. All right. And so when I evaluate this, that's going to be 2 squared minus x squared over 2 times 1 squared. See that? So I plug the 2 in for y, which gives me this. Plug the 1 in for y, which gives me this. And then that's dx. All right. And so this is going to give me integral 0 to 3. That's going to be what? 2x squared minus 1/2 x squared dx. And so this is going to give me what? 0 to 3. Now look, don't integrate each one of those terms. That combines 3/2 x squared dx. See, I can remember like terms from algebra, you can combine those. Okay. All right. So now it's just like you did when you first learned how to do integrals, right? So this is just going to be what? This is going to be 1/2 x cubed, right? Add 1, that's going to give me 3, and then divide by 3, so the 3's cancel, so I'm left with the 1/2, and that's 0 to 3. And so that's 1/2 times 3 cubed minus 0 cubed, which that is what? 27 over 2. All right. And there you have it. See, that wasn't too bad, was it? All right. So what do we want to do now? Well, we want to work another problem, another example. Now, wow, this looks familiar, doesn't it? Look at that, x squared y, x squared y. And look, 3, 0, 2, 1, 3, 0, 2, 1. dy dx, dx dy. So what I did is I swapped the order that I'm integrating. In this problem, I'm doing the same problem, same limits. I'm just integrating with respect to x first and then with respect to y. Up here in this problem, I integrated with respect to y first, and then with respect to x. All right, let's see if we get the same answer. All right, so I've got integral 1 to 2. Okay. Now, I'm integrating with respect to x first, so y is just treated like a number. So I'm going to add 1 to the exponent. That's going to give me x cubed, and then I'm going to divide by the 3. So that's going to be, I don't know, how do we want to write this? 1/3? I don't know. Let's write it y over 3 x cubed. All right. And that's from x equals 0 to x equals 3 dy. All right. All right, so now what do I have to do? I've got to work this thing. You see that? I've got to do that right there. All right, so that's going to give me integral 1 to 2 y over 3 times, now, you know how I did here? See how I had the coefficient here and I just left it out here and I plugged the 3 in for x and the 0 in for x? Look, I'm going to do the same thing here. This is like my coefficient right here. So I'm going to plug the 3 in for x, so that's 3 cubed minus 0 cubed dy. And so this is going to give me what? 1 to 2, that's 27. That's 0, 27, 3 goes into 27, that's 9y dy. All right. And so now we integrate this with respect to y. So that's going to be what? 9/2 y squared from 1 to 2, which that's going to be 9/2 times 2 to the 4th minus 1 squared. I'm sorry, I have no idea why I wrote a 4 there. 2 squared minus 1 squared, and that's going to give us, that's what? That's 4 minus 1 is 3, and 3 times 9, that's 27 over 2. We get the same thing, don't we? Whatever order we integrate them in. Now, another thing I want to kind of point out here is look at the work we did with this problem versus the work we did with this problem. Was it really that much of a difference? Nah, not really. Didn't make a whole lot of difference, did it? I mean, the work was about the same. Now, see here, I could have, you see, I didn't see the x squared over 2, the x squared over 2. When I evaluated, I just went ahead and wrote the x squared over 2 with both of them. I didn't do this. I didn't write x squared over 2 and then 2 squared minus 1 squared. See, I could have done that also, but I'm just showing you the difference. See the difference it makes? It's just a little bit easier to do this rather than this. That's all. Okay, and you can see when we did it like this, we had this, and then we did another step to combine them. But you know, if you did that here, you would have gone ahead and gotten 4 minus 1 is 3, so that's just 3/2 x squared, and you would have got it right there. So just a little tip right there. All right, we're going to do some more of those, don't worry. All right, so let's look at Fubini's theorem. If f is continuous on the rectangle, R is all the points x, y, such that x is between a and b, y is between c and d, then the double integral f of x, y, dA over R is the double integral a to b, c to d, f of x, y, dy, dx, which is equal to, and what's the difference in this one and this one? We changed. See, here we're integrating with respect to y and then x. Here we're integrating with respect to x and then y. But just make sure if you have something like this and you do switch the order that you're doing it, make sure that you're switching your limits on your integrals too. Okay? All right, so more generally, this is true if we assume that f is bounded on R, f is discontinuous only on a finite number of smooth curves, and the iterated integrals exist. All right, so let's look at this example here. You'll see some questions asked to you like this. Evaluate the double integral where R is all the points x, y, x is between 0 and 2, y is between 1 and 2. So let's do this. So let's just write the problem down. That's x minus 3y squared dA. All right. So remember delta A, that was the delta x times delta y. Okay. So what do we have here? Well, we've got the integral. Now, which one do we want to integrate with respect to first? Doesn't matter. We're going to actually work on both ways. We'll go with dy dx, and then we'll do it again dx dy. Okay. All right. So if I'm integrating with respect to y first. All right. So that means what? Well, that means the limits on my y need to be on the inside, and the ones on x need to be on the outside. See, look at this. See how the y is between c and d? So whichever one you're integrating with respect to first, that's what that needs to be. Those limits. See, just kind of look at it like this. Okay, I'm working this. If I'm doing dy, those limits need to be the y limits, cd. And then I'm just kind of working my way out. So then I got the dx, and that needs to be the ab out here because I'm doing that next after I do this in here. All right. And that's going to be x minus 3y squared times dy dx. Okay. You've got to get your limits right, what order you put them in, and the dy dx. All right. So let's see what we get here. So that's going to be 0 to 2, and we're integrating with respect to y first. All right, so x, we integrate x. So think about this. If you just had a 5 and you were integrating with respect to y, what would that be? That would just be 5y, right? Okay. And so what would that be? That would be xy, that's the antiderivative of this, minus, and then that would be minus, that's going to be y cubed divided by 3, that's just y cubed. All right, and that is from 1 to 2 dx. There I go again. I left it off, didn't I? Y equals 1 to y equals 2. Well, I know I forgot it. I would, like I said, I recommend putting the y equals so you know which variable you're plugging it into. Okay. All right. So this, we're going to get 0 to 2, and that is going to, okay, so we're plugging the 2 in for y. So that's going to be x times 2 minus 2 cubed, right? So I plug the 2 into here, minus, and now I got to plug the 1 in. So minus, well, let's plug the 1 in. That's going to be x times 1 minus 1 cubed. And that's dx. All right. So let's see what that gives us. That's going to give us 0 to 2. So that's going to be, look at this. Well, let's just write it out. That's going to be 2x minus 8 minus x plus 1. All right? Dx which that's going to be 0 to 2, and that's going to be x minus 7 dx. All right, and so now we've got this easy problem to do. That's going to be what? 1/2 x squared minus 7x from 0 to 2. So that's going to be 1/2 times 2 squared minus 7 times 2 minus. Now, I mean, you ought to know this by now. We got to plug the 0 in for x. But look, when you plug the 0 in, what's that going to give you? That's just going to give you 0, right? And so we get an answer of negative 12. All right. So there's the answer to that one. All right, so let's work this again. Okay, let's work this problem again. And see how much. Oh yeah, I got plenty. All right, so let's go. All right, so now I'm going to integrate with respect to x and then with respect to y. So I've got x minus 3y squared dx dy. All right, so x is between 0 and 2. So my 0 and 2 is going to go on the inside here, and then that's 1 to 2. All right, so now let's integrate this. That's going to be 1 to 2. All right. So I'm integrating with respect to x. So that means y is fixed. I'm going to treat y like a number. So the antiderivative of x, that's 1/2 x squared minus. Now look, you see this 3y squared? That's like just a number. So that's just going to be 3y squared x, and that is going from 0 to 2, and I've got dy. And I did it again, didn't I? How many more times am I going to do that in this video? X equals 0 to x equal 2. All right. Not being a very good example for y'all, am I? Forgetting that x equals 0 and x to x equal 2. Keep telling y'all to do it. Keep you from making a careless mistake, and then I don't write them down. So now I got to plug the 2 in, then I got to plug the 0 in. All right, so that's going to give me 1/2 times 2 squared minus 3y squared times 2 minus, and now I plug the 0 in. Now remember, I'm plugging this in for x. Now let's just think about this for a second. I'm plugging the 0 in here and here. That's just going to be what? 0. So that's 0 and then dy. And so that's going to give me 1 to 2. So that's going to be 2 minus 6y squared. I think I did that right. Yeah, 2 minus 6y squared. And now I'm going to integrate with respect to y. And so this is going to be 2y minus 2y cubed, and that's going to be from 1 to 2. And then we evaluate, that's going to be 2 times 2 minus 2 times 2 cubed minus, now we got to plug the 1 in, that's going to be 2 times 1 minus 2 times 1 cubed. And that is going to give me 4 minus 16 minus 2 plus 2, which that's actually going to be negative 12 again. Well, and that's what we should have got. That's what we got up here. Okay, so there it is. We worked it both ways. Okay. All right. So hopefully all this is making sense to you. All right, we got another one here. All right, we want to integrate double integral y times sine xy dA, where r, our rectangle, is 1, 2 by 0 pi. All right, so let's go ahead and set this up. So we got double integral r of y sine xy dA. So that is going to be, all right, so let's do 0 pi 1, 2, and that's going to be y times sine xy, and that's dy dx. See, I put my limits for y right here, dx. All right. So how do we go about solving this problem? Well, actually, if you look at this, we would have to use parts, wouldn't we? We would have to do integration by parts. So, you know, hopefully you remember how to do that. You would probably let u equal y and dv equal sine xy. Okay, and then have to go through all that and do that. But remember, we can integrate with respect to y and then x, or we can integrate with respect to x and then y. So, okay, so that we would have to integrate by parts. Well, what if we switch the order? What if we integrate with respect to x and then with respect to y? Would that be easier to integrate? Let's see. So let's set it up. So let's do this. Let's go 0 to pi, and then I've got 1 to 2 of y sine xy dx dy. All right, so, well, we can do that because y is like a number for us, isn't it? So this would be, all right, so just think about this. Remember, y is like, we're treating y like a number. So that's 0 to pi, and that's going to be what? Y times, now I need to, y times, so I need to integrate this. That's just going to be what? Negative 1 over y cosine xy. And that is from x equal 1 to x equal 2 dy. Okay, so let's just look at it. Just look at this right here. Y is just like a number, it's just kind of tagging along. So let's just suppose you had sine is equal to 2x. Okay, see, the y is like our 2. What's the antiderivative of that? That's what? Negative cosine 2x, and then you would have times the 1/2 out here, which would be negative 1/2 cosine 2x. Okay, and for those of you that don't see that, let me just do it. Let me do this. Okay, remember, you could let u equal 2x, and then du is equal to 2 dx. Remember that? Okay, so see, well, like if we're integrating this with respect to x, and we're off this problem right now. I'm just doing an example from back from when you first learned integrals. So u would get replaced with the 2x, and then I need a 2 dx, but I only have a dx, so I need to multiply by 2. So I'd come out here and multiply by 1/2, so that'd be 1/2 sine u du, and so that's negative 1/2 cosine u, which would be negative 1/2 cosine, and you plug the 2x back in. Okay, that's the long way about it. If that confused you and made no sense, then don't even worry about it. Okay, if you understood the first way that I showed you, just, you know, it's the antiderivative of sine is negative cosine, so you got the 2 there, so you need the 1/2, negative 1/2, or the 1/2 out there. That's all it is. Okay. All right. So that's where that negative 1 over y comes from. It's like a 2, you know, like that 2 in front of the x. All right. And so now we get, let's see, we got 0 to pi of negative cosine xy from x equal 1 to x equal 2 dy. I just multiplied that out and put it as negative 1. That's all I did there. All right, so let's see what we get here. All right, so I've got 0 to pi. So I've got negative cosine. Now I'm plugging 1 in for x. So that's going to be 1 times y, that's negative cosine y, minus negative cosine, and then I'm plugging the pi in for x, right? Plugging the pi. Oh, I'm sorry, not the pi, the 2. Plugging the 2 in for x. So that's going to be cosine 2y. And that's dy. And so this is actually going to give me the integral of, I'm sorry, man, that should be 2y, and this should just be y. So plug the 2 in for x, there's the 2y. Plug the 1 in for x, there's the 1y. Okay, for some reason, I just put them in backwards. Don't ask me why. That happens from time to time. All right, so this is going to be negative cosine 2y plus cosine y dy. All right, and so now we integrate with respect to y. So the antiderivative of cosine is sine. We got the 2 there, so that's going to be negative 1/2 sine 2y plus sine y, and that's from 0 to pi. All right. And so this is going to give us negative 1/2 times sine of 2 pi plus sine of pi I don't know why I put a parenthesis right there. All right, so I plug the pi in for y. And then minus, that's going to be negative sine of 2 times 0 plus sine of 0. Wow, that worked out pretty good for us, didn't it? Well, the sine of 2 pi is 0, the sine of pi is 0, the sine of 0 is 0, and the sine of 0 is 0. So this is just actually 0. All right? But, of course you need to know how to integrate this, but the one thing that we want to point out here that we want to emphasize on is, okay, so I said, okay, I'm going to do this, and I'm going to integrate with respect to y first, and then I noticed when I did that, I had a little more difficult integral to do. Okay? So, I mean, you may have some problems where you don't have a choice. You may have to just do parts, either way you do it. But, I looked at this, I said, oh, I got to do integration by parts. Don't really want to do that. So I switched the order up, and you can see it came out to be a little easier. All right, so let's look at this one. So find the volume of solid S that is bounded by the elliptic paraboloid x squared plus 2y squared plus z equals 16, and the planes x equal 2 and y equal 2, and the 3 coordinate planes. All right, so we need to, I guess we can kind of do a quick little sketch. Let's see what we've got. All right, so, you know, I'd have a, all right, so let's say I have this plane right here. Okay, so, you know, I could move this on up, and, you know, and this plane, this would be your plane x equal 2. See, all values are 2, so this would just keep going and go in all directions, infinite. Okay, and then we would have, and then you would have a plane. I'm sorry. Let me say something. Let me do that again. Never mind. And then you would have a plane y equal to all the values on the all the y values on the plane are 2, and you know that would go up. You know, you go up right here. Okay, and you would have this plane right here. Okay, but we've got an elliptic paraboloid that looks like this. Okay, so if we drew this up right here, you'd have something like this, and then it would maybe come like this, and then here, and then here. Okay, so you would have the elliptic paraboloid right here, and then you've got your planes here, and it's intersecting that and the coordinate and the 3 coordinate planes. So you're looking at your rectangle is right here. See, there's your rectangle. And so we can see we're going out to 2 here on the x-axis, going out 2 on the y-axis, and then there's your z-axis. Okay. So here we can see we've got z is equal to x squared plus 2y squared minus 16. Okay, we will solve this for, I'm sorry, that's not right. We've got z is equal to 16 minus x squared minus 2y squared. There's z. Okay, remember we need our f of x, y. Z, that's the height of the boxes. Okay, and we've got x is between 0 and 2. All right, now let me show you this. X is between 0 and 2, and y is between 0 and 2. See, the y is there's 0, between 0 and 2. X is between 0 and 2. That you can write it like this. What's the other way that we could write this thing? Well, we could write that our rectangular box is 0 to 2 by 0, 2. You know, whichever way you want to write it. Okay. All right, so let's go ahead and see what we get here. And so we're going 0 to 2, 0 to 2 of 16 minus x squared minus 2y squared, and we've got dx dy. And so there you go. You got it set up now. You know, if you can, it probably help to just sketch a picture. Okay. Now, you know, did we really need to draw that top part? Not really, but we did need these planes in here because that told us we're going from 0 to 2 and 0 to 2. Okay. And you might be wondering, well, why are you doing dx first? Why are you integrating with respect to x and then y? I don't know, I just am. It doesn't matter. Okay, on this problem, it's not going to matter which one you do first. Okay, all right, so let's see what we get here. So we've got 0 to 2, so I'm going to leave this here. See, the limits are the same on both of them. All right, and so this is going to be 16x minus 1/3 x cubed. I'm integrating with respect to x first. Now I've got the minus 2y squared. I'm integrating 2y squared. 2y squared, that's y is fixed. That's like a number there. And so that's just 2y squared x. And I'm going from x equals 0 to x equals 2 dy. All right. And so now we've got 0 to 2. And now we've got to plug all that stuff in. All right. So that is going to be 16 times 2 minus 1/3 times 2 cubed minus 2y squared times 2 minus, all right, so it's nice when that right there is 0 and we got variables everywhere, because when we plug the 0 in for x, all that's just going to be 0, and that's dy. And so this actually gives me 0 to 2. And look, when I multiply this out and do this, and I combine these two, that's going to give me 88 over 3 minus, and then this is 4y squared dy. All right. So there you have it. We integrated with respect to x. Now we integrate with respect to y. And so this is going to be 88 over 3y minus 4/3 y cubed, and that's from 0 to 2. And so that's going to be 88 over 3 times 2 minus 4/3 times 2 cubed minus, and then once again we plug the 0 in for y, all that goes to 0, and that ends up giving us 48 as an answer. All right, so let's look at the next thing. Oh, we got us some more information here. We got the double integral over r sine x. No, I'm sorry. Let's go up here. We got the double integral over r g of x times h of y. Oh, look at that. That equals the integral g of x ab dx times the integral hy dy from c to d, where this is your rectangle AB by CD. What is that? What did that just tell us? Oh, you know what? That's pretty neat right there, isn't it? So if you have two functions and they're multiplied together, if one of those functions is in terms of x and one of them's in terms of y, we can split them up, integrate them separately, and then just multiply the result. See that? And I wonder if that'll come in handy any. Well, let's look at this next example and see if it does. Look at that. Okay, so we've got the double integral sine x cosine y and dx dy. Now dA, that's equal 0 to pi over 2. See, we're 0 to pi over 2, 0 to pi over 2, sine x cosine y dx dy. So could you imagine having to try to integrate this thing right here with respect to x? I wonder if that would be very fun. Well, probably not, would it? But look what this tells us. This tells us that we can split them up. Because see, this is just in terms of x. This one's just in terms of y. And so this is going to be 0 to pi over 2 sine x dx times the integral 0 to pi over 2 cosine y dy. See that? Now, I know in this problem, they're both the same. is 0 to pi over 2. But you have got to make sure, if these are different, you've got to make sure you get the right limits on the integrals. Okay, this tells you on the x, this tells you on the y. All right, so let's see what we get. Well, what's the antiderivative of sine? That would be negative cosine x, and that's from 0 to pi over 2, times, and then the antiderivative of cosine is what? Sine, and that's from 0 to pi over 2. And so this is going to be negative cosine pi over 2 minus negative cosine 0. See, it's going to be this, that's this first one here, times, and then this one. That's the sine of pi over 2 minus the sine of 0. And this actually is going to give us, this right here is 1 times, and this right here is 1, which is 1. And there's your solution there. All right. All right, so let's look at this. All right, so we've got the average value of a function f of two variables defined on a rectangle R is, so remember you've done average value of a function before. That was, remember the average value when you did it before, that was, you know, you were integrating from, say, a to b of f of x dx. It was times 1 over b minus a. That would give you the average value. All right, but we've got a function of two variables. So the average value of a function f of two variables defined on a rectangle R is 1 over AR, double integral, over R, f of x, y, dA, where AR is the area of R. A is the area of the rectangle. Okay, the area of the big rectangle. The big rectangle, we're not breaking this one up into little squares. Okay, so let's look at this problem. It says find the average value of f of xy equal x squared y over the rectangle with vertices -1, 0, and there they are. All right, so we just need to look in the xy plane and plot these vertices here. All right, so let's do that. All right, 1, 2, 3, 4, 5, 1. All right, so I've got -1, 0. I've got -1, 5. I've got 1, 5. And I've got 1, 0. All right. And so there's my rectangle. So it's like I'm integrating this, right? X squared y, and that's going to be what? -1 to 1 by 0 to 5. See, -1 to 1, and then from 0 to 5. So there you have it. Okay. Now, my average value is the double integral. And, you know, it's not, whoop. I'm going to need to leave a little room there because remember, we got a 1 over the area of the rectangle. And we'll get that in a minute. All right, so I'm going, let's integrate with respect to y first. Okay, that's fine. So remember, so the y, that's going to go here. There's the x. And so that's going to be x squared y dy dx. And you know, if you wanted to, you can integrate with respect to x first. Doesn't matter. So I've got a r. See, I need my area of my rectangle. So what's the area of this rectangle right here? Well, it's just this times this, right? Well, this is 2. This is 5. So that's going to be 2 times 5, which is 10. So that's 1 over 10. And now we just integrate it. So this is going to give me 1 over 10 from -1 to 1. And so I'm integrating with respect to y. So what's the antiderivative of y? That's going to be squared divided by 2. So that's going to be x squared over 2, y squared. And that's going to be y equals 0 to y equals 5 dx. And so this is going to give me 1 over 10, -1 to 1. So that's going to be x squared over 2 times 5 squared minus 0 squared dx. And that is what? That is 25 over 2. So that's going to be 20. That's going to be 1/10 from -1 to 1. That's going to be 25 over 2x squared dx. All right, so I got 25 minus 0, 25 over 2x squared from -1 to 1. Integrating from -1 to 1. All right, so let's integrate this thing. So that's going to be 1/10. And this I'm going to get, let's see, 25 over 2. That's going to be x cubed times 1/3. And that's going to be -1 to 1. And so let's see, what is that going to be? Let's see. Let's see, that's 25 over 6. That's going to be what, 5 over 6? When I do all that, let me make sure. Yeah, 5 over 6. And then x cubed, I'm evaluating from 1 to -1. Well, so that's going to be 1 cubed minus -1 cubed. So that's just 1 plus 1. Oh, I'm sorry, that'd be a 2 there. So that would be 5 over 12. It's late in the video. My mind's going, I guess. So that would actually be 5 over 12 times 2, which would be 5 over 6. And so there's your answer. All right. All right. So let's look at this. All right. So this is an example from the book. And you know, I'm not going to get the same. I tried to redraw that picture in the book as best I could, but it is what it is. I'm not going to get the same answer that they get in the book. So if you recognize this picture in the book and you say, well, your answer is different than the one in the book, yeah, it probably is going to be, because my lines aren't exactly where the lines are in the book. So the values I'm approximating are going to be a little bit different. Okay. All right. So it says a contour map is shown for a function f. Use the midpoint rule with m equals n, which equals 2. So m and n are 2 to estimate the value of this double integral. Estimate the average value of f. All right. So let's look at this. So I need to break this up. And I can see already, let's see. So the midpoint is about right there. And then we'll say the midpoint's about right there. And then we got a midpoint about right there. So I'm guessing at these midpoints. And then we'll say we got another one right here. Okay, because it did tell us, it told us to use midpoints, right? That's what it told us. All right, so, well, what's the double integral? Well, this goes back to kind of what we did at the first. Remember, we got a point here, so we need what? We need the height, right? See, we need the height at this point times the area of each square. You see that? That's what we need. So we can see dA is equal to 2 times 2. See, it's 2 by 2, which is equal to 4. That's dA. See? M and N, they give you that. So it's like our delta X. See, our delta X times our delta Y. So that area there is 4. 2 times 2. And so we get, that's what they're wanting us to, f of x, y, dA. What does that equal? All right. So it's going to be 4 times. So that's actually the area of each square, right? That's the area of each square. Now, that's going to be times this height plus this height plus this height plus this height. So you can see that this right here, that's between the 20 and the 30, right? And so you can see here we are, you know, this side of 20, but we're closer to 20 than we are 30, so we'll just kind of estimate that to be 22. Okay, and this is what I'm saying. You know, even if you had the exact picture from the book, if I had it on here and I got those midpoints exactly, I might estimate a number different than what the book did. Okay, and then I've got plus, and then you can see here between 10 and 0, it's kind of close to 0 there, I guess. So I guess we make that maybe a 3, something like that. And then here, I'm between 22 and 10. I'm closer to 20 than I am 10. So maybe say that is maybe 18. And then plus this one, you can see I'm pretty close to 10 here. There's see, this is the 0, this is 10. So I don't know, maybe say plus 9. You know, like I said, you might pick 8 as the number. But anyway, so let me punch this in. 22 plus 3 plus 18 plus 9, and then times 4. And that gives me 208. Okay? And, you know, like I said, I tried to recreate this from the book as best I could, and I think the answer in the book's like 248, so you can see I'm off by some. But I think in the book, some of the dot, like this dot here in the book, I think is closer to 30 than what I had, than how I have it drawn. So, but anyway, you get the idea of what we're doing. That's the most important thing. And then they also wanted us to get the average value, right? Didn't it say that? Estimate the average value of f. And so the average value is the 208. Is the 208. So let's go back up here to average value and let me show you something. So remember, see, this right here is what we just calculated. That's what we calculated. That's that 20, whatever it was. What was it? 208. That's what we just calculated, the 208. But then I've got to do time. I got to multiply that by 1 divided by the area of what? The area of R, the rectangle. All right. So what's the area of this? Well, this is 4 by 4. So I got AR is 4 times 4, which is 16. So that's going to be times 1 over 16. And so let's see, divide that by 16, and that is actually 13. So that would be the average value. And guess what? That's it. We're done. All right, so I hope you enjoyed that. Hope you learned something. And you know, like I said, the double integrals, they're not bad. And the one thing I want to say to you, you know, if you're in Calculus 3, you know, I know some school on semester system, they have 3 calculus quarter systems, 4 calculus classes. So what I want to say, if you're in the 3-dimensional calculus, multivariable calculus, look, it's not really any different than what you learned in single variable calculus. The main thing that you have to know and understand to do is you got to know how to take derivatives, and you got to know how to integrate. That's the 2 important things. Okay? I mean, you can see all this lesson here, all it was integrating. That's what we did. All right? We just had a little more stuff tagging along with it, but that's really all we did was integrate. And actually you can see that the integrals we actually did, they were easier than some of the integrals you did back in single variable. Now they may get tougher as we go, but you know, the ones in here weren't bad at all. All right, so hopefully this video helped. Check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I'll see y'all in the next one.